Thank you for the introduction. Once more, my name is Landon. I am from Professor Amit Lall's Sonic MEMS lab at Cornell University. Today, I'll be presenting on feature-based machine learning for predicting resistances in printed electronics. And bear with me just in the beginning, so I can get this. Right, so here is the outline for the talk today. I'll briefly go over the motivation for the project, and then the background, and then some of the methods that we use to create electronics training data sets. And then I'll talk about the prediction of printed electronic resistances using various machine learning models. And then finally, I'll conclude with future work. Yeah. So the motivation for using printed electronics, as most of you know, is that it can offer cheaper and faster alternatives to traditional manufacturing in some circumstances. Oh, am I not talking loud enough?
Yeah, okay.
I can't do both of these ends. Can everyone in the back hear me? Fine. Okay. Sorry. Yeah. So other than their advantage in terms of speed and affordability in some circumstances, they also offer you the capability to replace components that have gone bad in remote environments, such as like submarines or the Arctic or in the sky. But one of the major drawbacks of printed electronics is that most of the more affordable commercial printer options, they employ inherently chaotic processes, and they use inaccurate control and feedback systems. And this often leads to significant variation of your final results. So the aim of this project is to try to work with the more affordable options that we already have in-house, but improve upon the results using feedback and machine learning models that are trained based on resistance values and other geometric data to then predict certain outcomes, in this case, resistor values. So now I'll talk about some the similar work. Some companies have already started improving P outcomes using these strategies. For instance, Nanodimension has been using DeepCube's proprietary deep learning engine since they acquired them in 2021. And then in academia, there hasn't been any attempts like so intense as Nanodimensions, but they are better documented because they're not proprietary. So here's a couple of the most similar works. So Wiley et al., they trained models to predict some resistances of HAP resistors using an Optimec HAP printer, and then also this other group, they trained models to predict resistances from a piezo inkjet nozzle. But one of the things that makes our approach different from them is that we created an automated resistance probing system for quickly measuring many resistances and using a really large data set in order to train our ML models. And then also all of these other groups that I have read about, they use 2-point resistance probing, whereas we use 4-wire measuring. Yeah, so our goal was to perform the study with the resistor arrays printed using two common P technologies, one being thermal inkjet printing the printer that we have on hand is the Bosch Factory SP2, and then also extrusion-based or paste type direct ink writing. For example, the Volterra V1. A note about the SP2 is that it has extreme print variation. So the Volterra boards eventually ended up making up the majority of our training data set because the amount of usable boards from the Bosch Factory was limited. Even though I'll still talk about the Bosch Factory for a moment for those of you who aren't familiar with it, just to touch on its capabilities, because I will have a little bit of a comparison between the two printers from some preliminary resistance measurements. So the Bosch Factory is right here. It allows you to print with dielectric ink and conductive ink. Used to, they also shipped carbon-based resistive ink, but they no longer sell that. And then you can also dispense solder paste with the printer and pick and place components. Although this uses like a camera to detect. Okay. It uses a camera to detect the orientation, so it's kind of finicky, and you save a lot more time just by placing them yourself. And then it also has solder reflow capability. And then for the Volterra, like I said, it's an extrusion-based CP printer. Here's a little video of it doing its thing. It's kind of like a miniature icing gun for cakes. You can also dispense solder paste with it, and it has solder reflow capability. And you can drill vias, but we won't be employing any of those capabilities in this presentation. So now I'll talk about some of the methods employed to create the PE training data set. So here is the DOE board. It's a 4-pad resistor. This is the Volterra version and the SP2 version. And then here's a full board with the variable gaps and widths. And here is the full assembly for the automated resistance probing station that we built. We use an LPKF ProtoLaser U3 as a pulse laser cutter to cut to hatch the top and bottom of the copper flat F4 board and make this modular pogo pin interchangeable PCB for doing the actual probing. And then we use a push button to actually have a repeatable contact force and detect that we hit the PCB. Here's the connection schematic. We use the Keithley 2400 SMU to actually measure the 4-point resistance values. And here are the steps of operation. So the ARPS, and I can go through those a little fast because you can see the steps in this video. I'm just going to play half of it. So the system uses G-code. It's a synchronous setup. So basically, the way that the PC, the Python code is able to get feedback from the system is through a USB GPIO board that's taking digital input from the push button switch. And here's the Keithley, just taking resistance measurements. It takes several measurements per resistor, and then it averages them. Slide. Here are some preliminary resistance measurements using this setup for the Volterra and the Bosch Factory boards. They had an average standard deviation at milliamps measuring current of 16.1 microohms and 16.4 microohms respectively. And then also we found that the mean resistance variance was the same at any given current for each board, indicating that the measurement isn't set up limited. And then for the visual information through our machine learning models, we use a high resolution Epson D50. We scanned at DPI 4800, which gives us a pixel size of around 5.425 micron. Here are some basic challenges associated with optical metrology using this method. We have alignment and segmentation, and then differentiating high contrast regions and normalizing contrast variations across large spaces. Here's an example of our rotation correction image process. And here are some grayscale and segmented cells from the boards. Some more information about the optical process. Here is the actual ML method section. So instead of blowing up this project and having to use like Amazon Cloud GPUs or something to get an answer, we didn't want to feed in full images to our neural network. Rather, we wanted just one or two scalar input that capture the texture of the silver printed areas. And so these are the two equations we came up for that. So these are two scalars calculated pixel wise through the full image for each cell. We call them like constant horizontal, constant vertical. Let me know if you want if you have questions about this figure later. We'll talk about it. So we employed two different scenarios for the ML learning algorithms. Scenario one was to use a single printed board where the printing parameters are the same. And then for scenario two, we did cross-board testing. So we had multiple boards printed with different settings, and we tried to randomly sort them and then train on all of that data as with this one. So for scenario one, here are results using 5 different ML methods. We have linear regression with polynomial features, lasso regression, and then lasso regression with polynomial features. And then we also have a neural network with 2 hidden layers, first being 100 nodes, and then the second being 10 nodes. It's fully connected. And we see that we have sort of a convergence as the training size increases. And then for the scenario two, this is our RMSE for the cross-board testing versus training size for the 5 different methods. So for the future work for this project, what we're interested in doing is moving away from using the expensive and slow Epson scanner for collecting the image data. We've developed using an endoscopy camera, which has a very close working distance, less than 1 millimeter. We have a system that is able to actually capture the print very close up as it's printing in real time. And since we're downscaling the images already and grayscaling them, we should be able to do these computations in real time and learn as you're printing, and even be able to detect whenever issues are arising in your printed structure. So that's the future goal. Finally, I'd like to acknowledge all of the people who made this project possible, and all of our sponsors, and brief mention of the funding, and then finally questions.